Tropias, or heterotropias, and Phorias, or heterophorias, are both examples of strabismus. Strabismus is an eye turn. Don't confuse an eye turn with amblyopia, which is a lazy eye. Lazy in the term lazy eye refers to the vision. It means that the opposite eye has a much better visual acuity, and this eye is lazy because it isn't pulling its own weight. The other eye is doing all the work. Strabismus, on the other hand, is an eye turn. The eye is turned or in a misaligned position. That being said, of course, the two often go hand in hand because if a person has a manifest strabismus, vision in that turned eye will need to be suppressed in order to avoid double vision. So a strabismus often is also a lazy eye. What is the difference between a tropia and a phoria? A tropia is manifest, meaning it is always there. A phoria is latent, meaning it is not always there. Okay, let's talk about a few of the directions in which these strabismus can present. These are diagrams of tropias, and you can see the left eye in each example is misaligned, has a strabismus. I'm going to get more into the difference between tropias and phorias in a minute, but for now, just take my word for it. These are all tropias, and note the names for the positions. The one in the upper left, that patient has a left eye that turns in nasally. The prefix for that type of eye turn is iso, meaning in. And just under that one, the lower left there, the patient has a left eye that turns out temporally, and the prefix for that one is exo. And then the two on the right, the upper right, the left eye turns up, of course, that's hyper, and down is hypo. The two on the right are examples of vertical strabismus, and those are a little bit different than the horizontal. Also, we have another word, ortho, which means straight, and that'll be used as a prefix in front of either tropia or phoria. There are many tests to detect and measure strabismus. In this video, we're only going to go over 5. The cover-uncover test, the alternating cover test or cross-cover test, Hirschberg's test, Krimsky's test, and the Prism and alternating cover test. First, I want to talk about the cover-uncover test because I said I would talk more about the difference between tropias and phorias, and this test shows it pretty well. The only drawback is that it won't detect a very small tropia or phoria. For that, you have to do the alternate cover test. But this is a pretty good test, and it also tells you the direction. Okay, this patient has an esophoria. How do I know that? Well, I don't necessarily yet, but what I do know is when I'm looking at both eyes, unoccluded, they both look straight. When a patient has a tropia, you will see a deviation when both eyes are uncovered. So as soon as you look at the patient, you should be able to tell that one of those eyes are turned. With the phoria, with both eyes unoccluded, they should both look straight. You won't really be able to tell until you tease that phoria out. So let's do it. I made this occluder transparent so you can see what happens to this phoric eye when it's occluded. See there's the ESO. Of course, in real life, you won't be using a transparent occluder, so what you have to pay attention to detect the phorias is when you uncover the eye. As soon as you uncover that phoric eye, you should see it move back into the aligned position and lock into fusion with the other one. Okay, let's watch another one. This patient has a hyperphoria, so you see that left eye move upwards when it's occluded and back into place when the occluder is removed. This patient has a hypertropia. And again, usually you can tell if your patient has a tropia as soon as you look at them. You should be able to see that one of the eyes, at least one of the eyes, is deviated. And unless it's a very small tropia, And when you're doing the cover test with a hypertropic patient or any tropic patient, when you cover the deviated eye, there's no movement. That eye is just going to remain when you cover it, when you uncover it, no movement in either eye. It's when you cover the opposite eye, the fixed eye, that you'll see movement. And when the occluder is removed, that eye returns to its deviated position. Before we go on, I want to mention Hering's law. Hering's law states that when an eye muscle contracts, the yoke muscle in the opposite eye also contracts. They receive equal innervation, which just means when you look to the left, you don't look to the left with just your left eye. Your right eye also looks to the left equally. There are 6 positions in which these eyes have these type of coordinated movements, and 6 pairs of yoke muscles correspondingly. These are known as the cardinal positions of gaze, and again, each position is controlled by a pair of yoke muscles. Okay, there's 6 pairs of yoke muscles. Those are good to know. Also, it's a good thing to take note of right here that the straight up gaze and the straight down gaze are not yoked. So when you're looking straight up, both eyes are looking straight up, or both eyes are looking straight down, but those are not movements that rely on yoke muscled pairs. Okay, the reason I wanted to show you all that is because now we're going to do the cover test with an esotropic patient. And I'm going to use a transparent occluder so you can see what happens underneath the occluder. Okay, that right eye, when the left eye was occluded, did exactly what we thought it was going to do. It went from the eso position and it straightened out into a fixed position. But look what happened under the occluder. The left eye turned in nasally. Now why did it do that? Well, in order for the right eye to straighten out from the eso position turned in nasally to the straight position, the muscle that had to be engaged to do that, had to be innervated, is the right lateral rectus. That is paired with the left medial rectus muscle, their yoke muscle. It's yoke muscle. So when the right lateral rectus received innervation to turn that eye straight, the left medial rectus received equal innervation and turned the left eye in nasally. The reason I'm mentioning this is because I want you to pay attention to when you remove the occluder, because that left eye is going to go back into the fixed position, and you're going to have to notice that that's not a phoria, that's a right esotropia. And watch what happens here. This patient has an obvious right esotropia, which straightens out as the left eye is occluded, and then when the left eye is uncovered, it does not return to its deviated position. Now the tropia has moved to the left eye. That's called an alternating tropia when that happens. And just to recap, when you're testing patients with phorias and tropias, you usually have to prompt a phoria to go into its misalignment. But for the tropia, you're going to see that right off the bat, and what you're going to do when you're testing it is just prompt it to go into its aligned position. The next test is the alternate cover test. And the alternate cover test can't determine whether the patient has a tropia or a phoria, but it can detect some phorias and tropias that are a little bit too small to be seen with the cover-uncover test. And the way that the alternate cover test is performed is just like it sounds. The eyes are covered alternately. You're only allowing that uncovered eye a few seconds, enough time to fixate and focus on the target before you're placing the occluder back over that eye and allowing the other eye to focus and fix on the target. And this patient here, I'm not seeing any movement whatsoever. This patient is what is called orthophoric, has orthophoria. Orthophoria and orthotropia are not the same thing. Orthophoria would be what you might call a normal eye. The eyes are straight, no deviation, they're working together, they're maintaining fusion. With orthotropia, the eyes are also straight, there's no deviation, but with the orthotropia, there's no proof of fusion. And that's for another video. Okay, now we'll talk about how to write all this down. And starting with the directions of deviation, capital E for ESO, capital X for EXO, capital H for hyper, and a small h for hypo. And then to distinguish between atropia and aphoria, with atropia you're going to write a capital T, and with aphoria you're not going to write anything. There's just going to be the absence of the T. And in intermittent tropia, you're going to put parentheses around the T, and we haven't discussed that yet, and I don't think we'll do in this video. I'll save that for the next one. D for distance, of course, N for near. And for near, you can also use that little prime symbol, and its absence would mean distance. Up at the top there, you'll see that triangle. That is the Greek symbol for delta, the Greek letter delta. And that's used in superscript, and that denotes prism diopters. That's the measurement of prism, and we're going to be doing that in just a minute. And then, of course, L for left, R for right, and F for fixed. And I wanted to mention pupil sizes really quickly. The pupil size can vary, and of course it's going to vary in the individual depending on whether the pupil is constricted or dilated. But in the following tests that we're going to do, we're going to go with a 4 millimeter pupil. We're just going to estimate the pupil to be 4 millimeters.
Okay, now that you've got all that, it's time for a quiz. See if you can tell what these abbreviations mean.
Vertical deviations are often noted using the higher eye. For example, if you have a patient whose left eye is looking straight ahead and the right eye is looking downward, that could either be called a right hypotropia, but more often it would be noted as a left hypertropia. That's for vertical deviations. Okay, the next test is Hirschberg's test, and this gives a rough estimate of the magnitude of the deviation. It's good for those patients that aren't able to cooperate, follow directions, such as children, infants. To do this, you're going to need a light source, such as a pen light, and you want to take note of where the reflection of that light falls on the eyes, the corneal reflex, or little white dot on the eyes. And this is one of the tests where I mentioned earlier, we're going to assume that the pupil diameter is 4 millimeters, and 1 millimeter will be equal to 15 prism diopters, or 7 degrees. In this first example, the corneal reflex is seen at the edge of the pupil. And in the next example here, you see the corneal reflex in that right eye in the center of the iris. And in the third example, you see that corneal reflex at the edge of the limbus, and that's what you're looking for, that little white dot, the corneal reflex. So the way you estimate the measurement in this one is that if we have a 4 millimeter pupil, 4 millimeter diameter, the corneal reflex that's at the edge of the pupil, of course, would be 2 millimeters, and 1 millimeter is 15 prism diopters, so 2 is 30 prism diopters. So that is written as 30 prism diopters, left hypertropia. With the second example here, that corneal reflex is now in the center of the iris, approximately 2 additional millimeters, so 4 millimeters from the center of the pupil, or 60 prism diopters, right exotropia. In this third example, we now have a corneal reflex approximately 6 millimeters from the center of the pupil, or 90 prism diopters. It is left esotropia. When you're doing the Hirschberg, it's beneficial to draw some mental horizontal and vertical lines to kind of line up in your mind where those pupils fall in relation to one another. You may see that you'll have more than one tropia. In this example, for instance, this patient has a left esotropia, also a left hypertropia. So if you draw those lines in your mind, it's a little bit easier to determine the deviation. In a person with normal ocular alignment, the light reflex lies slightly nasal from the center of the cornea. The reason being the fovea lies slightly temporal to the actual anatomic axis. So when a light is shown into the cornea, it causes a reflex on the visual axis just nasal to the center of the cornea, about 5 degrees or so. It's called the angle kappa. It's the angle that's formed at the intersection of that visual axis and the pupillary axis. When the reflex is slightly nasal like that, that's called a positive angle kappa. You can also have a negative angle kappa. That's when the fovea lies slightly nasal to the optical axis, and the corneal reflex then lies temporal to the center of the pupil, negative angle kappa. What you need to pay attention to, though, is that they're both symmetrical in both eyes, whether you have a 5-degree positive angle kappa or 5-degree negative angle kappa. Just watch for the symmetry. The next test is Krimsky's test. It's similar to Hirschberg's, but Prism is used to quantify, which means measure the deviation. Prisms bend light rays so that a prism held over the eye will refixate that light onto the retina. It'll bend it and fixate it into a different position on the retina. There are 2 methods for doing Krimsky's test. The original Krimsky's test, where a prism is held over the deviated eye, but more common now is the modified Krimsky's test, where a prism is held over the fixating eye. We're going to start out with the modified Krimsky's, whereby the prism is held over the fixating eye, not the deviating eye. Now, this method relies on Hering's law. Remember, equal innervation. When a muscle in one eye is innervated, causing movement, its yoke muscle in the other eye also receives innervation to move, causing movement. This patient has a left exotropia. We're going to start out by holding a 10 diopter prism over the fixating eye and watch what happens to the corneal reflex in the left eye. We see that it's shifted a little bit, but not quite enough, so let's try a stronger prism. Let's try 20 diopters, and again we see a little bit of shift, but we're not quite there yet. So let's try a 30 diopter prism, and there we have the corneal reflex centered in the pupil on that left eye. So this patient has a deviation of 30 prism diopters. Okay, let's talk a little bit about what has gone on here. You can see that both eyes have moved. That's obvious. The left eye has gone from the exo position to the fixed position, and the right eye has gone from the fixed position out to the exo position. Why is that? Well, the prism has prompted the movement. By placing the prism in front of the fixed eye, the prism bent the light rays so that they were no longer focused on the fovea. In order for that right eye there to see its target, it had to move so that the light rays are once again focused on the fovea. So the right eye has done the movement, causing the left eye, by Hering's law, to be equally innervated and to straighten out. So now you can see that the corneal reflex is in the center of the pupil in both eyes, and they've both moved in order to gain that position. The prisms in reality are more of a square shape, or they're attached in a prism bar. Mine are trapezoidal, and I did that just so you could see which is the apex and which is the base. And the notations are as follows: BI base in, BU base up, BO base out, and BD base down. That's how they're written. Let's move on to the second version of the Krimsky test. Okay, this time we're going to hold the prism over the deviated eye. And we're going to start out with a 10 diopter prism. And that's not doing it. Let's try 15. Okay, not quite. 20. Not quite. 30. Looks about right. Let's try 40. Oh, that's too far. You can see that's a little bit too far. That's gone past center. So we'll go back to 30. This version of the test isn't quite as favorable as placing prism over the fixated eye, simply because it's a little more difficult to see the corneal reflex through the prism. While it's not very important which eye we hold the prism over, it's very important which way we hold the prism. If we're holding the prism over the deviated eye, as we just did, the apex, the smaller, thinner end of the prism, should point in the direction of the deviation. Since we note the prisms by their base, that means the base is away from the deviation, of course. For instance, if we have an eye that's deviated temporally, the exodeviation, we're going to point the apex in the same direction towards the temple, which means that the base would be in. Okay, same thing if we have an esodeviation, meaning that the eye is pointed in nasally, the apex is going to be pointed in nasally as well, and the base will be out. It'll be base out. Same thing for up and down. When we hold the prism over the fixated eye, however, we're going to do the same thing with a horizontal deviation. We're going to hold it the same way. So if our right eye, for instance, had an exodeviation, our right eye was pointed out temporally, but we're going to hold the prism over the left eye. We're going to hold the apex towards the left temple, just like as if we were holding it over the right eye, we would hold it towards the right temple for an exodeviation. If we're holding it over the left eye, we're going to hold it towards the temple. And that's for horizontal. However, for vertical deviations, we're going to do the opposite. If we had a left hypotropia, for instance, if we were going to hold the prism over that left eye, that deviated eye, we would of course point the apex down, because the eye itself, it's a hypotropic eye. We're going to point the apex down and base up. But since we're holding it over the opposite eye, the fixated eye, we're not going to hold the apex down. We're going to hold the apex up, and it's going to be a base down prism. And that goes for the vertical deviation. Same thing for a hyperdeviation. If we have a left hypertropia and we're holding the prism over the right eye, we're going to hold it base up. Now for the Prism alternating cover test. But before we do that, we're just going to start on this patient with the cover-uncover test. And we see no movement here with the cover-uncover test. So now let's try the alternate cover test. And as we do this, oh, we see movement. Yep, definite movement.
So now we move on to the Prism alternating cover test. This is going to be used to measure either Tropias or Phorias, and we're going to do the same alternating cover test again, but this time we're going to place a prism over either eye, doesn't matter, while we do the alternating cover test. We're going to increase prism until we no longer see any movement. So let's start with a 5 diopter prism. And I'm seeing movement here. So we're going to need to increase it. We'll try the 10 diopter prism, and again, I'm seeing a little movement. Let's see what we get with the 15 diopter prism, and this looks like I'm not seeing any movement here. It looks like this patient has a 15 diopter deviation. And that's it. We've been through all 5 tests, and there they are. I want to end this video with just a few last facts about Phorias and Tropias. Phorias are often asymptomatic. A patient might not even know they have a phoria. You'll have to, again, break fusion during testing in order to see it. Or if they have any symptoms, what might happen is, like, for instance, they are tired, it's at night, they worked all day on the computer, came home, helped the kids with their homework, 10 o'clock at night, they're sitting down in front of the TV and with a bowl of popcorn, and they look down and at the popcorn, look up at the TV, and oh, there's double vision there for a second. Or it might be headaches, eye strain, asthenopia symptoms. With tropias, there are several different types of tropias. Some of them are the comitant, which is the same in all gazes. The incomitant, that degree varies according to the field of gaze. A and V patterns are examples of these. We have the constant tropia, which is the same degree, always present. Intermittent, which is not always present. That can be a little bit more difficult to diagnose because sometimes it's there, sometimes it's not, sometimes it seems a tropia, sometimes it's a phoria. We have the alternating, which changes eyes, and of those 5, we mentioned the comitant, the same in all gazes. We mentioned the constant, same degree, always present, and we did mention briefly the alternating, where it changes eyes. I do want to talk about the incomitant and intermittent. I'll do another video for those. And thanks for watching.